This is Module 2 of Mechanics of Materials Part 2. Today's learning outcomes are to define the qualifications for a structure to be treated as a thin-walled pressure vessel, give some examples of thin-walled pressure vessels, and then determine a method that we'll use for analyzing thin-walled pressure vessels. This is where we left off last class as far as the way that we have for a general analysis approach. And so we're taking an engineering structure. In this case, we're taking this gas storage tank, which we're going to model as a thin-walled pressure vessel. We're going to look at the external loads applied to that structure. In this case, the external loads will be pressure inside the vessel due to the liquid or gas. And that's going to generate internal forces and moments, which will in turn cause stresses and strains, and we'll be able to use that information to determine the structural performance of our engineering structure. And so thin-walled pressure vessels, let's look at a section cut. So here I've taken a cut, and here is the cross-section. If I look at a side view, we're going to say that thin-walled is defined as when the ratio of the wall thickness to the diameter of the vessel is so small that the distribution of normal stress in the cut surface is essentially uniform throughout the thickness of the shell. And that's not precisely true because there's a pressure on the inside, so stress is actually maximum on the inside surface and minimum on the outside surface where we have a free surface or no stress. But we're going to model it such that the distribution is essentially uniform. And so because we have a thin-walled pressure vessel, that means that the outside diameter and the inside diameter are not going to be that much different. And so I'm just going to call them the diameter, and I'll give it the symbol D. And if D, the diameter over the thickness of the outside of the shell or vessel, is greater than or equal to 20, we're going to define that as a thin-walled pressure vessel. So here are some examples of thin-walled pressure vessels. They may be boilers, gas storage tanks, perhaps pipelines, even blimps, could be spray cans. All of these are good examples of what could be defined as thin-walled pressure vessels. So now we need to look at the analysis techniques we're going to use. And I want you to recall back to the first course in this 4-part series of Mechanics of Materials. And I'm going to ask you, what should we use, plane stress or plane strain, in analyzing these thin-walled pressure vessels? You're going to have to use your engineering judgment in modeling, and this is a very important step in the engineering process, and you're going to have to be aware of the assumptions you make. I often say that engineering is as much an art as it is a science, and the art part is taking a real-world engineering structure and figuring out how we're going to model, analyze, and potentially even design. So as a review, let's go back and look at what we talked about as far as plane stress in the first course in this series. Plane stress said that there was no stress in the z directions, and so we only had stress in the plane or in the xy plane. And all real-world situations, all structures are three-dimensional, but we can make the plane stress assumption to simplify the analysis without significantly affecting the results that we get. And we said that a common example of plane stress might be used in the analysis of thin plates such as the skin panels on aircraft wings. Also, as a review, we talked about plane strain. Plane strain is when we have no strains in the z direction, but there can be stresses in the z direction. And so this is structures where we have a large relative dimension in the z direction with restraints to prevent strain in the z direction. And so some examples I gave from my first course were dams, retaining walls, tunnels, or bars, tubes compressed by forces normal to their cross-section, so they were not allowed to extend. So knowing this review of plane stress and plane strain, what do you think we'll use to analyze? Which of those would be best to analyze thin-walled pressure vessels? And what you should come up with is two-dimensional or plane stress. And the reason for that is if we look at a pressure vessel, on the outside surface, if we call the perpendicular to the outside surface, or the normal to the outside surface as being the z direction, there are no stresses on that outside surface. And it's a thin plate, similar to, or thin engineering structure, similar to what we would see in the skin panels of aircraft, maybe a little thicker, but again, no stresses in the Z direction gives us a plane stress condition. And so that's the method that we're going to use as we move along and analyze and design thin-walled pressure vessels. And I'll see you next time.